Hi class, this is Sir Alex again. Welcome back to our lesson in General Chemistry 2. We are opening a new lesson, lesson 11. Today we are focusing on 11.1, which is chemical equilibrium. So today we are discussing what is chemical equilibrium and how we kind of like measure for equilibrium of a reaction. Okay, so at the end of today's lesson, basically the whole lesson of lesson 11, what I want everyone to be able to understand is be able to explain chemical equilibrium, especially in terms of the reaction rates of the forward and the reverse reaction. So we are going to talk about the chemical equilibrium and what basically is forward and reverse reaction. Also for you class to be able to calculate the equilibrium constant, we are going to talk about equilibrium constant as well and the pressure or concentration of reactants or products in an equilibrium mixture. And lastly, for everyone to be able to understand and state the Le Chatelier principles and apply it in quantitatively to describe the effects of changes in pressure, concentration, and temperature on a system at equilibrium. So the main focus of today's lesson would be the first part and a little bit about the second part. The third part will be in more or less on our next lessons. So let's head on and discuss what is chemical equilibrium and what is reversible reactions. So what I want everyone to understand is when we talk about reversible reaction, it simply means that the reaction can proceed both forward or backwards in direction. What do we mean by that? So, for example, an example of a reversible reaction is the formation of nitrogen dioxide from dinitrogen tetroxide. So from N2O4, we can make 2 moles of NO2. But what is reversible reaction? And what is forward and backwards direction? Forward reaction is basically meaning from your reactions or from your reactants going to your products. That is forward direction. Backwards direction is basically the reverse reaction of your forward reaction. So from your products going back into your reactants. And you may have not been aware, but that is actually possible. You can have an equation or chemical reaction wherein it goes back and forth between reactants to products or products to reactant. And one example of that is the formation of nitrogen dioxide or NO2 wherein from dinitrogen tetroxide we can make 2 moles of NO2, and from 2 moles of NO2 or nitrogen dioxide we can make 1 mole of N2O4. So if we graph that, this is what is happening. So we start with N2O4 since it's our reactant right here. So we have some concentration of N2O4, this blue graph right here, this blue curve. And at the beginning, so time, at the start, we have this where we have 0 here. We have some concentration of NO2, but we have 0 concentration of NO or N2O4. We have some concentration of N2O4, but we do not have any concentration of NO2. That is because we started basically with 100% N2O4. And then as the reaction goes forward, we kind of like discuss something, we discussed this a little bit, wherein as the reaction proceeds, we start to create products. And what happens is we use some of the concentration of our reactants, in this case N2O4. That's why, as you can see, the concentration of N2O4 slowly starts to decrease. At the same time, we are increasing the concentration of our product because we are creating this product from some concentration of N2O4, or in this case, which is our reactants. And we've discussed about this when we talk about stoichiometry, for example. No, so in this scenario, we are making from 1 mole of our reactant, we are creating 2 moles of our reactant. That's why in this case, there's a higher increase, no? There's a faster increase of the concentration of NO2 as opposed to the decrease of N2O4. And this point right here is the point wherein we have equal concentrations of both. But that is not the chemical equilibrium. When we talk about a chemical equilibrium, it is the situation wherein The rate, we are talking the rate, so meaning how fast, no, not the concentration. We are not talk When we talk about equilibrium, we are not talking about the situation wherein there's equal concentration of reactants and products. When we are talking about chemical equilibrium, this is a situation wherein the rates of production of the reactants or the products are equal, basically, or happening at the same time. So what is happening is, for example, here, so the N2O4 will keep decreasing until such a time it reaches a state of equilibrium wherein the lines flatten out. This flatten out because the concentration of N2O4 and the concentration of NO2 are now basically constant. This is because the concentrations are not changing, creating this equilibrium. Um, what I want also to remember, this does not mean that the reaction stop. What is basically happening in this situation is that there's going back and forth, no? It's basically as N2O4 proceeds to make 2 moles of NO2 at the same rate, at the same speed, some concentration of NO2 are becoming N2O4. That is what we call equilibrium or chemical equilibrium. I hope I've explained that clearly, but again, I want to emphasize that when we talk about equilibrium, we are not talking about an equal concentration of reactants or products. What we are talking about is we are talking about the rates wherein the formation of NO2 is equal to the formation of N2O4. Basically means the production rate from N2O4 to NO2, the speed is equal to the speed of NO2 going back to N2O4. So that is the reversible reaction. And all of the chemical equations actually has a tendency towards a state of chemical equilibrium. Most of the chemical equations that you see something like this, they have a tendency to favor a situation wherein the rates of the production of the product and the rate of the product going back as reactant is basically equal. Again, this is the rate po, it's not the concentration, because if you can see here, this from the previous discussion that we've had, from this alone, we know that the entropy here is higher at NO2, no? Not just because of the phase changes, but because we have more number of particles in our product. So which means we have more particles in our um, gas. What does or in our product? What does that mean is that the reaction favors the product, and we can even say it here: the reaction favors the product because we have more concentration of our product than in our N2O4, making this reaction a spontaneous reaction. No, but again, when we talk about equilibrium, I really want to emphasize this and I want to really drive it home. We are not talking about a situation wherein the concentration are equal. We are talking about a situation wherein the rates of the production of the products and the rate or the speed wherein the products are coming back as reactants is basically equal. They are at the same rate. Now, since the forward and the sorry about that noise, but since the forward and reverse reactions are happening at equal speed, the concentrations of both reactants and products are constant and at equilibrium. So as you can see here, they're constant because they're not changing. They're not changing because kahit na nauubos yung NO2 pabalik sa N2O4, some concentration ng NO2 nawawala din at pumupunta sila sa NO2. So pabalik-balik lang siya. So you can think of this as the particles going back and forth, no? Some N2O4 becomes NO2 and some NO2 goes back to becoming N2O4. And we've talked about this. It's kind of similar to our discussion in biology of dynamic equilibrium. Remember when we talk about osmosis and concentration gradients, there is a situation wherein the amount of particles passing the plasma membrane and the amount of particles going back is basically equal. That's what we call the dynamic equilibrium, no? Even though the products or the concentration of the products and reactants are constant, the reaction is still ongoing. It does not mean the reaction stopped. It just means the reaction is happening forward and backward at the same rate. So that is what we call chemical equilibrium. That is what we call reversible reaction. Now let's talk about a magnitude or some number that we call equilibrium constant. So equilibrium constant, we can measure this using the molar concentrations of all the species in the reaction. When we talk about species, this is basically the chemicals that you use during the chemical equation or in the chemical equation during a chemical reaction. So identifying or being able to identify the molar concentrations. You guys remember molar concentrations is moles per liter. Identifying the molar concentration of each of the products, you can identify equilibrium constant. So you may be asking, why do I need to identify this equilibrium constant? This is because equilibrium constant can be used to determine which of the which side has higher concentration. Do I have higher concentration of products or do I have higher concentration of reactants during my equilibrium reaction? So when my reaction arrive at an equilibrium situation or in a dynamic equilibrium, which side do I have more concentration? Do I have more products or do I have more reactants? And you can identify that using the chemical or using the value of the equilibrium constant. If you have equilibrium constants of 1000 or more, so very large number of equilibrium constant, which we are going to start calling Kc, because equilibrium constant is a mouthful. So if we have 1000 or more Kc, what this means is we have higher concentration of products. So just remember that. So if you have 1000 or even more or very large number of Kc, you have more concentration on the products during the equilibrium dynamic. If you have 0.001 or even less than Kc, it usually does not become negative, no? You usually have very small. It becomes really, really, really small. So at 0.001, what does this mean is you have a higher concentration of reactants. So do you guys remember our discussion when you have Kc of higher than 1, you have a situation where it favors the product. This is this part, no? If you have a situation wherein you have less than 1, as you can see here, you have less than 1, it's really, really small, the concentration or the reaction favors the reactant. In this case, you have higher concentration of reactants. But if you have a Kc between 0.001 and 1000, it just means it has a significant concentrations of both sides. It does not mean that they're equal. It just means that there's a significant amount of products and there's a significant amount of reactants. And the equation or the mathematical expression that we can use to solve for equilibrium constant or Kc is this situation right here, no? So if you have this general equation right here, so let's say this is our general equation, this is our general reversible equation. We know that this is a reversible equation because of the double headed arrow in between them. So if you only have if you only see one arrow heading in one direction, that means it's not reversible. But we know this equation is reversible because of this arrow. That's one good reminder to identify whether the reaction is reversible. So what you want to do is basically take your product and divide it by or take the concentration of your products and divide it by the concentrations of your reactants. So you take the concentration, we're using molar concentration, moles per liter. We're taking the molar concentration of one product and then raising it, or basically raising it to the power of the coefficient, multiplied by how many products you have, as long as those products are in the numerator and they're raised to however the number of their coefficients are. And then divide all that to the molar concentration of your reactants raised to whatever the number of their coefficient is. Now in this case, we have a molar concentration of C raised to some small letter c because that is its coefficient, multiplied by some concentration or some molar concentration of D raised to some small letter d because that's its coefficient, divided by to some molar concentration of A raised to small letter a, multiplied by some molar concentration of B raised to small letter b. So using this formula, you can measure the equilibrium constant. And one note that I want you guys to take now, remember, is that we only use chemical or equilibrium constant in a situation wherein the equilibrium dynamic is reached. No? The reversible reaction is in a situation wherein the products becoming reactants is happening at the same rate that the products are going back as reactants. One another note that I want you guys to remember about the equilibrium constant is that equilibrium constant is very specific at a temperature. No, if you change the temperature of this chemical equation of the reaction, Kc changes. So usually the temperature should not change, because if you change the temperature, you will change your equilibrium constant. Another thing that I want you guys to remember is when we are dealing with pure solids and pure liquids, including the solvents, those are not included in this uh, equilibrium expression. No? Because if there's a lot of reason for this, but if you see, for example, like pure solids, so if you see like S or L, then we usually do not use that in the equilibrium expression. Most of the time, what we have to use is aqueous solution or AQ or gas. So if you have AQ or gas, then that's what you have to use to solve for the equilibrium constant. And also remember, we don't have a unit for Kc. We do not, yeah. So just this is a relief for you guys. You do not have to memorize any unit for Kc. And lastly, to get the proper value of Kc, the coefficient must be written in the smallest possible whole number. So this cannot be, for example, you multiplied both sides by 2. Make sure that the small letters A's, B's, C's, and D's are the smallest possible whole number value. Okay, sample problem. Let's have, and now from our discussion, let's take our discussion and apply it to the sample problem. So let's take a look at the equilibrium reaction that takes place between sulfur dioxide and oxygen. So this is our sulfur dioxide, and we have oxygen, and we are creating sulfur trioxide. Let me use my pen. Okay, so this is basically what we have, and then this reaction is happening at some temperature T. I did not, it's in the module, I just forgot to write it, but this is happening at some temperature T. We do not care about the temperature, but they give us the molar concentration for each of your species. So you have some molar concentration for your sulfur dioxide, for your oxygen, and for your sulfur trioxide. Now, what we want to measure is measure Kc. So this is basically the given na. What we just want to write now is habang tinatanong sa atin, we are being asked what is the equilibrium constant. And the formula that we have to use is the formula that I showed you earlier. So you would have Kc is equals to the molar concentration. In this case, what we'll have is A, B, and C. So it's a molar concentration of C divided by some molar concentration of A raised to A, some molar concentration of B raised to some B. Now let's try this solution. So we have Kc is equals to, we just basically have to substitute the values. No? So we have is the concentration of our Sulfur trioxide, since it's our product usually goes on the numerator, we have 1.1 molar. So we have 1.1 molar raised to the constant or to the coefficient of our product, which is 2. And then we have A, which is sulfur dioxide, and the molar concentration of our sulfur dioxide is 0.90 molar raised to 2, because that is the coefficient. And then we have our molar concentration for oxygen, which is 0.35 molar. And it doesn't have any, I mean, it does have, it has one. So we'll just put one there. It's not necessary because this automatically means one anyway. So just plugging in that, it's quite easy, right? Just use your calculator and you can solve for Kc. And in this situation, our Kc is 4.3. Again, we don't need units because we don't write units for equilibrium constant. And as you notice, our equilibrium constant is between 0.01 to 1000. What this means is we have significant concentrations on both sides. Okay, significant concentrations on both sides. So Kc is between, Kc is, this is the shortcut for between. No? Between 0.001 to 1000, which means there are significant concentrations on both sides. Another way that we can actually check the reaction equilibrium is using what we call reaction quotient. So reaction quotient. Or which we denote with letter Q. So what is reaction quotient? Reaction quotient is basically the same as Kc. The only difference is that with Kc we use it during the time that the reaction is at equilibrium na. As for quotient, we use it at any point in the reaction. So using the reaction quotient, you can use it anytime, basically whatever the concentration of the chemicals are at any given point during the reaction process. So what that means is during the chemical reaction process, sometimes you can measure your concentrations of your reactants in your products, for example, placing them in a different vessel, and then you can solve for the reaction quotient. So for example, we've taken our samples and put it in a different vessel, and then we measure the concentrations and they gave us these concentrations. So what I want you to remember now is when we solve for quotient, reaction quotient, at any point in time, this is one way that we can identify whether the reaction is at equilibrium. Now, because the reaction is at equilibrium if we solve for the quotient of the reaction during at any point in time, and if it happens to be equal to Kc, then that reaction at that point in time is at equilibrium. And this is because if you want to solve for the reaction quotients, it's basically the same. It's basically the same formula or expression. You would have A raised to A and B raised to some B. And just plugging in the numbers, you would get 2.2 raised to some 2. And you have 3.6 raised to 2 multiplied by 0.087. And if you actually plug this in the calculator, you would also get 4.3. So what this means is at some point we're in the reaction or at these concentration, these situation tells us that at these concentrations the reaction is also proceeding at an equilibrium constant. So when Q is equals to Kc, the reaction at that given point, because again we can use this at any given point, we can only use this at equilibrium, but when our Q is equal to Kc, the reaction is at equilibrium at that point. Okay, so I hope that is clear. So Q is basically, you can, yeah, you can use it to check Kc, but it's more like to identify whether a reaction is at equilibrium or not. I hope that is clear. It's quite simple naman. What is equilibrium, or what is equilibrium constant? Now let's try this another sample problem. Let's consider the equilibrium mixture of N2, O2, and NO. We know that the equilibrium constant, so in this case, let's write our given. As for our problem, they already gave us our Kc, so it means we're now solving for Kc. Our Kc is 3.4 times 10 raised to negative 21 at a particular temperature. So at the constant temperature, we cannot change this temperature, otherwise this would change. And we also know that the molar concentration, so they gave us the molar concentration for our N2, our reactants basically. So they gave us the molar concentration of our reactants is 0.1 molars for both. So they have equal concentrations, equal molar concentrations for both species in our reactants. So, and then what are they asking us is basically the molar concentration of our products. So how much products basically do we have? And the formula that we have to use is the same formula. We have some Kc is equals to some C raised to some C, and they have concentration of A raised to A and B raised to B. Okay, so now before let's solve this, let's look at these Kc now. So as you can see, our Kc is less than 0.001. What does this tells us? This tells us that our reaction favors our reactant. Our reaction favors reactant. Therefore, our NO concentration, or the reactant, the concentration of our product should be less than the concentration of N2 or O2. So as you can see, so from Kc we already derived this information. Now what we have to do is just solve this to confirm our guesswork, to confirm this notion, to confirm this surmise. Okay, so what we're solving is NO. So we have the chemical equation of this, and then just plugging in the number. Our C is NO. The situation is raised to 2. And then we have N2. It doesn't have any coefficients, or it has a coefficient of 1, so that's raised to 1. And we have O2 and also raised to 1. Since we are solving for N2, we just have to rearrange our equation. That gives us the concentration of NO raised to 2 is equals to Kc multiplied by the concentration of N2 multiplied by the concentration of O2. And then we have to square both sides because our N2 is raised by 2. Therefore, our concentration for NO is equals to the square root of Kc multiplied by N2 multiplied by the molar concentration of O2. And the molar concentration of NO is equals to the square root of 3.4 times 10 raised to negative 21 multiplied by 0.1 molar multiplied by 0.1 molar. And that gives us an answer of, if you plugging in on your calculator, is will give you an answer of 5.8 times 10 raised to negative 12 molar. And let's confirm our answer. Is this smaller than 0.1? Hell yeah, it's smaller by a lot. Therefore, our answer should be correct, no? Because we know from our Kc alone, since it is less than 0.001, that our reaction favors the reactants. So we should have more concentration on our reactants than our concentration in the product. So that's how we use molar concentration, and that is chemical equilibrium. If you guys have any questions, do not hesitate to message me or ask me anytime through Messenger. I hope it's clear. We're going to continue on with our discussion next week, and have you guys have a great